This lecture is about the recommender systems. So far we have talked about a lot of aspects of search engines. And we have talked about the problem of search and the ranking problem, different methods for ranking, implementation of search engine, and how to evaluate the search engine, etc. This is partly because we know that web search engines are by far the most important applications of text retrieval, and they are the most useful tools to help people convert big raw text data into a small set of relevant documents. Another reason why we spend so many lectures on search engines is because many techniques used in search engines are actually also very useful for recommender systems, which is the topic of this lecture. And so overall, the two systems are actually well connected, and there are many techniques that are shared by them. So this is a slide that you have seen before when we talked about the two different modes of text access, pull and push. And we mentioned that recommender systems are the main systems to serve users in the push mode, where the systems would take initiative to recommend the information to user or to push the relevant information to the user. And this often works well when the user has a relatively stable information need, when the system has a good knowledge about what the user wants. So a recommender system is sometimes called a filtering system, and it's because recommending useful items to people is like discarding or filtering out the useless articles. And so in this sense, they are kind of similar. And in all the cases, the system must make a binary decision. And usually there is a dynamic source of information items, and you have some knowledge about the user's interest, and then the system would make a delivery decision whether this item is interesting to the user, and then if it is interesting, then the system would recommend the article to the user. So the basic filtering question here is really, will this user like this item? Will you like item X? And there are two ways to answer this question, if you think about it. Right? One is to look at what items you likes, and then we can see if X is actually like those items. The other is to look at who likes X, and we can see if this user looks like one of those users, or like most of those users. And these strategies can be combined. If we follow the first strategy, to look at item similarity in the case of recommending text objects, then we are talking about the content-based filtering or content-based recommendation. If we look at the second strategy, then it's to compare users. And in this case, we're exploiting user similarity, and the technique is often called collaborative filtering. So let's first look at the content-based filtering system. This is what a system would look like. Inside the system, there will be a binary classifier that would have some knowledge about the user's interest, and this is called a user interest profile. It maintains this profile to keep track of the user's interest. And then there is a utility function to guide the user to make decisions. And I explain the utility function in a moment. It helps the system decide where to set the threshold. And then the accepted documents will be those that have passed the threshold according to the classifier. There should be also an initialization module that would take a user's input, maybe from a user's specified keywords or chosen category, etc. And this will be to feed the system with the initial user profile. There is also typically a learning module that would learn from users' feedback over time. Now note that in this case, typically a user's information need is stable, so the system would have a lot of opportunities to observe the users. If the user has taken a recommended item, has viewed that, and this is a signal to indicate that the recommended item may be relevant. If the user discarded it, it's not relevant. And so such feedback can be a long-term feedback and can last for a long time. And the system can collect a lot of information about the user's interest, and this can then be used to improve the classifier. Now, what's the criteria for evaluating such a system? How do we know this filtering system actually performs well? Now, in this case, we cannot use the ranking evaluation measures like a map, because we can't afford waiting for a lot of documents and then rank the documents to make a decision for the user. And so the system must make a decision in real time in general to decide whether the item is above the threshold or not. So in other words, we're trying to decide the absolute relevance. So in this case, one commonly used strategy is to use a utility function to evaluate the system. So here I show a linear utility function that's defined as, for example, 3 multiplied by the number of good items that you delivered minus 2 multiplied by the number of bad items you deliver. So in other words, we could kind of just treat this as almost in a gambling game. If you deliver one good item, let's say you win $3, you gain $3. But if you deliver a bad one, and you will lose $2. And this utility function basically kind of measures how much money you will get by doing this kind of game, right? And so it's clear that if you want to maximize this utility function, your strategy should be to deliver as many good articles as possible and to minimize the delivery of bad articles. Yeah, that's obvious, right? Now, one interesting question here is how should we set these coefficients? Now, I just showed a 3 and a -2 as the possible coefficients, but one can ask the question, are they reasonable? So what do you think? Do you think that's a reasonable choice? What about the other choices? So for example, we can have 10 and -1, or 1 minus 10. What's the difference? What do you think? How would this utility function affect the system's threshold decision? Right? You can think of these two extreme cases, 10 minus 1 versus 1 minus 10. Which one do you think would encourage the system to over-deliver? And which one would encourage the system to be conservative? Yeah. If you think about it, you will see that when we get a big award for delivering a good document, you incur only a small penalty for delivering a bad one. Intuitively, you would be encouraged to deliver more, right? And you can try to deliver more in hope of getting a good one delivered, and then you'll get a big award. Right? So on the other hand, if you choose 1 minus 10, you don't really get such a big prize if you deliver a good document. On the other hand, you will have a big loss if you deliver a bad one. You can imagine that the system would be very reluctant to deliver a lot of documents. It has to be absolutely sure that it's not a non-relevant one. So this utility function has to be designed based on a specific application. The 3 basic problems in content-based filtering are the following. First, it has to make a filtering decision. So it has to be a binary decision maker, a binary classifier. Given a text document and a profile description of the user, it has to say yes or no, whether this document should be delivered or not. So that's a decision module. And there should be an initialization module, as you have seen earlier. And this is to get the system started. And we have to initialize the system based on only very limited text description or very few examples from the user. And the third component is the learning module, which has to be able to learn from limited relevance judgments, because we can only learn from the user about their preferences on the delivered documents. If we don't deliver a document to the user, we would never know. We would never be able to know whether the user likes it or not. Right? And we can accumulate a lot of documents and can learn from the entire history. And all these modules would have to be optimized to maximize the utility. So how can we build such a system? And there are many different approaches. Here, we're going to talk about how to extend a retrieval system, a search engine for information filtering. Again, here's why we've spent a lot of time to talk about the search engines, because it's actually not very hard to extend a search engine for information filtering. So here's the basic idea for extending a retrieval system for information filtering. First, we can use a lot of retrieval techniques to do scoring, right? So we know how to score documents against queries, etc. We can measure the similarity between a profile text description and a document. And then we can use a score threshold for the filtering decision. We do retrieval, and then we kind of find the scores of documents, and then we apply a threshold to see whether a document is passing the threshold or not. And if it's passing the threshold, we're going to say it's relevant, and we're going to deliver it to the user. And another component that we have to add is of course to learn from the history. And here we can use the traditional feedback techniques to learn to improve scoring. And we know Retrieval can be used for scoring improvement, right? But we have to develop new approaches to learn how to set the threshold. And we need to set it initially, and then we have to learn how to update the threshold over time. So here's what the system might look like if we just generalize the vector space model for filtering problems, right? So you can see the document vector could be fed into a scoring module, which already exists in a search engine that implements vector space model. And the profile will be treated as a query, essentially. And then the profile vector can be matched with the document vector to generate a score. And then this score will be fed into a thresholding module that would say yes or no. And then the evaluation would be based on utility for the filtering results. If it says yes, and then the document will be sent to the user, and then the user could give some feedback. And the feedback information would be used to both adjust the threshold and to adjust the vector representation. So the vector learning is essentially the same as query modification or feedback in the case of search. The threshold learning is a new component that we need to talk a little bit more about.